Good day everyone, welcome to our per group discussion. Alright, let's start with our first objectives. The definition of a group. So let's learn the basics. A group in abstract algebra is a set of equipped with an operation that satisfies four fundamental properties: closure, associativity, identify element, and inverses.
Right, so closure means that when you combine two elements using the operation, the result is still within the set. In addition, associativity means that the way we group elements in an operation doesn't affect the result. The identity element is an element in the group such that combining it with any other element leaves the other element unchanged, while inverses mean that for every element there exists another element such that their combination results in an identity element. Am I right?
You got it right, Maria. Now, for example, our set of positive integers and our operation is multiplication. Closure hold because multiplying any two positive integers results in another positive integers. Associatively is an evident because the multiplying three integers together gives the same result regardless of how we group them. And identify the elements is 1 because multiplying by any integers by 1 leaves the unchanged. For inverse, every positive integers has a multiplicative inverse. For instance, the inverse is 5 is 1 over 5 because 5 times 1 over 5 is equal to 1.
What a comprehensible explanation, Tristan. So, the positive integers under multiplication form a group.
That is correct, Maria.
Moving on to the next objectives, proving elementary properties of groups. So let's prove associativity using the positive integers under multiplication. For any integers a, b, and c, a times b times c equals a times b times c. So can you help me, babes?
Demonstrate this by rearranging the terms and using the commutative property of multiplication. So the quantity of a times b times c is equal to a times the quantity of b times c, which is equal to a times b times c, confirming associativity. This property holds true for all positive integers, showing that associativity is a fundamental property of groups.
So we've proven one of the elementary properties using the positive integers under multiplication.
Hello guys! Hearing from all of you, I am thrilled to share my learnings about how to construct Cayley tables for finite groups. So, by definition, a Cayley table is a way to represent the binary operation of a group in a table format. So each row and column corresponds to an element of a group, and the entry in each cell represents the result of applying the binary operation to the corresponding elements. For instance, let's create a Cayley table for a small finite group. So consider the group of positive integers under multiplication modulo. We have 4 elements, 1, 2, 3, and the identity element 4, since 4 modulo 4 is 0. And each row and column in the Cayley table will represent one of these elements. We'll fill in the table by performing multiplication modulo 4 on every combination of elements.
Wow, that's amazing. This visual representation will help us see the groups pairtized within context and modular arithmetic.
You are not mistaken, Tristan.
Now, let's use the properties we've discussed earlier to prove a proposition. Consider the group of prime numbers under multiplication. We know that identity element is 1 because multiplying any number by 1 leaves it unchanged. Is there anything you would like to note, Nisaya?
Yes, there is, Maria. Every prime number has a multiplicative inverse that is also a prime number. So if we take any prime number p, its multiplicative inverse is 1 over p, which is also a prime number.
Excellent answer, Nisaya. Therefore, in the group of prime numbers under multiplication, every element has an inverse that is also in the group.
As abstract algebra deals with algebraic structures such as groups, rings, fields, and modules, the use of technology in abstract algebra may not be as prominent as in some other fields. There are still ways to leverage technology for communicating solutions. One notable application is the use of Computer Algebra System, or the CAS, and specialized software. For instance, software like Mathematica, Maple, or SageMath can be employed to perform complex algebraic computations, visualize abstract algebraic structures, and generate interactive demonstration. These tools can assist mathematicians in verifying proofs, exploring examples, and gaining a deeper understanding of abstract algebra concepts.
That is correct, babes. So, utilizing technology to communicate solutions in abstract algebra would involve mentioning the use of computer algebra systems, specialized software to perform computations, visualize structures, and aid in the exploration and communication of abstract algebraic concepts. So in conclusion, through our discussion on binary operations, groups, basic group properties, and employing technology to convey our solutions effectively, we have comprehensively addressed all the learning goals and proficiency in these principles and methodologies will empower us to further explore group theory and its mathematical applications.